Yeah, that's my kind of night. Okie dokie, ladies and gentlemen, happy What's Good Wednesday. We didn't have Thomas on the Good Tuesday, so what's good today on Wednesday? Yes?
I had a work shadow yesterday, or job shadow.
Oh, very cool. Very exciting. What else? What's good?
Italian sausage on the pear. So good.
I've had 17 Lurch's Donuts so far.
Oh, 17?
Yes, so that's Lurch's Watch 2023. And I do run 1 mile for every donut I eat. So I've got 17 miles. I'm over half a marathon. Not all at once.
There was like, where do you think we'll see Mr. Heller at the fair? And I was like, I don't know. And it was a Lurch's donut stand.
And I was literally right there. Yep, I was there. I'm working tonight. I'll be working at Bob's tonight. So stand right beside Lurch's. So come say hi. I'll sell you the Wayne County Giant. It's like a $23 thing, which is like a pile of stuff. What else? What's good? Emily, anything good? She's not telling the truth because it's her birthday. Happy birthday to you. Happy birthday to you. Oh, this is getting recorded. Happy birthday, dear Emily. Happy birthday to you. Happy birthday. Come on up, get a piece of candy. Happy birthday.
You were hoping and praying.
She thought that I was like, anything good with you? No, nothing good with me today. Did you guys win last night? I was supposed to line judge last night. But I got, my wife, the van died. So she was like driving down 201 and the van just died. So I think the alternator went bad. But like nobody got hurt, no one was injured. So that's the good thing out of that. It's getting fixed today, I think. Not gonna be cheap.
Did you have problems with that van last year?
Well, last year I just had a lot of maintenance all at once. So I ended up having to get new tires on both my cars the same week. So I ended up like putting like $5,000 worth of maintenance into both my cars in a week. But Honda did send me a little bag, a little Honda bag as a thank you for spending $5,000. Yeah, it was a little bag. Hi, Braden. Okay, test. Test was pretty good. Take a look at the test. First page was pretty straightforward. There is no letter C on your version. I wanted to make it a little bit shorter to make sure you guys had enough time. The main thing people missed right here. All right, I asked for how many atoms. I asked for how many atoms. Many of you gave me how many molecules of chlorine and not atoms. So if you didn't do that last step, you had like 4 point something instead of the 9.791. So that was 2 points if you forgot that step. I did one just like that in the notes. I think I did. Number 2, at the bottom, also pretty straightforward as long as you balanced it correctly. That was 36.8 grams, 3 sig digs. If you start with 3 sig digs, you've got to end with 3 sig digs. Any questions on page 1? Page 2. Page 2. Empirical molecular formula. Pretty good. Pretty good on this. The empirical formula was PnCl2. The molecular formula should have been P5N5Cl10. A couple people had a mistake at this point. Either they got the wrong molar mass, which messed them up. But that problem was with 2, 4, 6, 9. That was worth 12 points on that one. Questions on number 3. 4, going back to the lab now. How do you know? How can they conclude the hydrate was heated? Well, in our lab, it had to change by what? By less than 0.01. Some of you actually wrote that again. I didn't count it off. Because here it actually changed by less than 0.001. So some of you even wrote by less than 0.01. I didn't count it off, but technically changed by less than 0.001. So it's sufficiently dry. If it's changing by less than 1/1000th of a gram, we can say it's dry. Second one, this took a little bit of thinking, so some people missed this one. That's not what I meant. I was not a slam, okay? A different student heats the hydrate, and some of the solid spatters out. This spattering will have what effect on the calculated mass of the water lost? The mass of the water lost will be greater. It will be greater because the solid that spatters out had what with it? Water. So you needed to say greater and have some kind of decent explanation for why. That was worth 2 points. I took off a point if you did not have that correct. AP loves doing questions like this. And we do so many labs, my people always get it. My people always get it. Because you guys know labs, you guys know how to identify lab error, you know how to fix it. Questions on this page? Next page. Unfortunately, some people identified the wrong limiting reactant. So if you did, and you did the rest of the math correctly, I didn't take off all the points because that's like not cool. This one was worth, let's see, 4, 5, 9, 11, 13. That was worth 14 points. So I did not take off all the points if you identified the wrong limiting reactant. Because if you identified this wrong, everything else is wrong. Okay? So just make sure you guys are good with identifying the limiting reactant. I know for every one of these, I need 1.5 of those. So for every one of these, I need 1.5 worth of this. Well, that's about 1, right? So I needed about 1.5 of this. That's not 1.5. That was a limiting reactant. And then a couple people forgot to subtract for the excess. They just left it at the used. So to get the excess, you have to take the used minus the original to get your excess. Questions on that one? Why are you smiling?
I'm just scared. Number 6.
Guys, number 6. Number 6. I gave you the impure, and I said, what is the percent? What is the percent? So you had to figure out the part. All you had to do was the following. Balance it correctly. People did that. And then run what you know. You have 0.1964 grams of this, right? Run that 2 grams of that. That would be the pure.
I was literally
That's
on
it.
the right track.
Part divided by
Oh
total
my
times
God.
100, 1.4%.
That is so frustrating.
That's all you had to do. So it was 1 line of stoic and then a percent. So once again, overthinking here. So where mistakes were made,
I didn't know. Almost the time
this. All right? This. If it is impure, here's the problem. A lot of people tried to start with this number. All right? If it's impure, you can't run it in stoic, right? You can't run it through stoic because it's not pure. So you have to start out with what you know. So you run grams of this, 2 grams of pure Tl2SO4, divide that by the total, 1.467%. Very few people got that. But I was pretty cool on grading that. I don't remember how many points I took off, but I think it was not super many. That was number 6.
The most annoying thing about that problem was having to write thallium iodide because the L and the I look exactly.
Well, you didn't have to write that out. You could have just written that. Does that make sense on 6?
Yes.
Okay. And then the bonus, if you attempted it, if you want to see that, it was kind of fun. Once again, same as last chapter, one of these again if you had time, 30.8%. And then this one at the bottom was super fun. 1 massive line of stoic.
No.
Those were just 2 points.
It takes more time to read the problem.
Yes, Jaway literally wrote on his paper, I don't have time for this. So, questions on the test. Has everybody done the AP Classroom part of it?
No.
Okay, don't do it now. Okay, do it by tomorrow. Okay, do it by tomorrow so we can get that done. Today and tomorrow, we're doing notes. If anybody wants to bring snacks tomorrow, that would be great, just for fun. I don't know why. I think it'd be nice to have snacks on day 2 of notes in a row. Questions are up there for the chapter. 89 and 90 you will not be able to do until probably a week and a half or so, because I'm not going to get to those notes this week. It's 3 days of notes for this chapter. Friday we have lab prep. We will be in lab all week next week. 5 days.
So the homework, like,
Yes.
spread across 2 days?
The homework, I just couldn't fit it all in one.
Okay.
So that's due the day of the test, which is not next week or the week after. So you got time.
Oh my God.
Yes.
What's in the parentheses?
It says balance 89 and 90, which you will not know how to do that for a week or 2.
Okay.
So if you're working through problems, I would definitely save those for the end. I'll tell you when you'll be able to do those. Cool? How was cross country? Good. How was football game? The band sounded good on Monday at the fair. Obviously the best. What else? Volleyball won last night, right? Anything else exciting from the weekend? Okay. Get out your notes. Let's roll. Let's roll.
Seriously, right? I don't have time for this.
Yeah, I said.
Today we are starting chapter 4. All right? Chapter 4, which I call More Reactions.
How many?
I call this More Reactions / Solution Stoic. More Reactions / Solution Stoic. So let's start super basic and define a solution. How would you guys define a solution? What is a solution usually made of? What is the solution usually?
Solvent and a solvent.
And what is the solvent usually? Water. A solution is usually water-based. You're going to get 12 solutions starting in lab on Monday. And we know that Aubrey just said that water is the universe, it's known as, you probably heard this before, the universal solvent. The universal solvent. Who has heard that before? Probably everybody. All right, and what does a solvent do in a solution? It dissolves, right? The what? Not the solvent, the solute. The solvent dissolves the solute. The solvent dissolves the solute. Why? Why is water known as the universal solvent? What is special about water? Everything has a bunch of properties.
Maybe.
Why is water special?
Because we're made of it.
Well, other things have like a slightly negative charge.
You're kind of on the right track.
Is it because of the bonds? I don't know.
Let's draw water. Let's draw water. Here is H. Here's an H connected to an O with 2 lone pairs, right? What is hydrogen's ionic charge? It's +1. +1. And what is oxygen's ionic charge? -2. Do you see that there is 2 clear sides in water, in a molecule of water?
Yes.
This side is what?
Positive.
Positive. And this side is what? Negative. What is that called in chemistry?
Oh, polar.
Polar. Water is polar. Water is polar. It has an uneven distribution of charge. It has 2 poles. It has a positive side and it has a negative side. All right? That's why you've probably heard this: like dissolves like. Like dissolves like. So things that are polar dissolve things that are polar. Things that are nonpolar can dissolve things that are nonpolar. But things that are nonpolar don't like to mix with things that are polar. For example, water's polar. Give me an example of something that's not polar that wouldn't mix with water. Oil. All right? Oil. All right? I don't know why I said it like that. Oil. Don't ever say like dissolves like on the AP test, okay? That's not going to get you any points, okay? It's not going to get you points, but it's helpful to help you remember. Freshman year and last year, you should have made a graph something like this. Had solubility on the Y, you had temperature on the X, you had a line. I juggled this day. Anybody remember when I juggled? Okay. Had ABC, solubility and temperature. Do you guys remember me juggling? Emily, do you remember that? You don't remember it, do you? Wow. How do you not remember that?
I don't remember that in that knowledge.
You don't remember.
Well, I juggled just 2 years ago. Anyways, so this is my solubility graph. So that means point A, it's above the line. So what's point A considered? Supersaturated, right? Remember how I juggled and I could only hold 2 balls and then I had to put energy in to juggle all three? Yes. B is on the line, so it's saturated. And C is under the line, which means I can still dissolve more. So C is unsaturated. It is unsaturated. Do you remember that?
What is the word on the x-axis?
Temp.
Yeah.
Temp. Well, some of you didn't have physical science as a freshman, so this might be kind of new. But that's what you need to know. So we're going to make a little table here of things that dissolve easily and things that don't dissolve easily. So here is things that dissolve easily. We're going to make that on this side. And on this side, we're going to make things that don't dissolve easily. So there's my little chart. So, anybody ever had an example of something that dissolves easily, like a scientific type of compound that might dissolve?
NaCl.
What type of compound is NaCl? Ionic. Ionic solids dissolve easily. I like that. Examples: salt, lithium chloride. All of those things dissolve very easily. Another thing that dissolves easily are strong acids. Strong acids, put an asterisk here, you got to memorize these. You have to know what the strong acids are in AP chemistry. The strong acids are the following. I'm going to list them out. Sulfuric acid. HI, what would that be? Hydroiodic acid. I'm putting these in order for a reason. HBr would be hydrobromic acid. HNO3 would be no more hydro. That's nitric acid. HCl would be hydrochloric acid. And the last one is HClO4, which you may not know off the top of your head. That is perchloric acid. Perchloric acid. Those are the 6 strong acids. The way I remember this is, so I brought no clean clothes. What do I mean by that? Sulfuric, hydroiodic, hydrobromic, nitric, hydrochloric, perchloric. That's how I remember the 6 strong acids. So I brought no clean clothes. Or you can make up your own, but that's how I remember it. The thing about strong acids completely dissociate. What does the word dissociate mean? What does the word dissociate mean? What do you think it means? Yeah, Aubrey just did this. Break apart, yes. If you put a strong acid in water, if I put hydroiodic acid in water, it completely breaks up into hydrogen ions and iodine ions. It completely dissociates. Strong acids completely dissociate, so therefore they dissolve easily in water. The other thing that dissolves easily is my strong, guess what it is? Strong bases. So also my strong bases. There's not a lot to memorize here because these are basically just your alkali metal hydroxides. So these are your alkali metal hydroxides. Can anybody give me an example of an alkali metal hydroxide? LiOH, lithium hydroxide, or NaOH, sodium hydroxide, or potassium hydroxide, KOH. And guess what strong bases also do? What?
Completely dissociate.
Yes! Strong bases completely dissociate. So when a strong base hits water, it completely breaks apart. Those are things that dissolve easily. So my thing should have, there we go. Now we have one side of the chart. Things that don't dissolve easily, it's basically the opposite. So my opposite of strong acids is going to be what? Weak acids. Weak acids do not like to break up. Couple of my favorite weak acids. H3PO4. You don't have to memorize these, by the way, because if it's not a strong acid, it's a weak acid, okay? Everything else is a weak acid except for those 6. Another one would be H2CO3, and another one would be HC2H3O2. Well, this one is phosphoric acid. Anybody know where I find that? Coke. This is carbonic acid. Anybody know where I find that? Pepsi. All right? And this is just acetic acid, which you'll find in vinegar. This is HC2H3O2. That is acetic acid. How do acids taste? Remember this? Good. By themselves, they taste sour. Okay? Usually acids taste sour and bases taste bitter.
Do we need to know that they taste different?
No.
Okay.
But it's something helpful. Now, do any people here like to drink pop? So, specifically ladies, okay? So you have to be careful because your carbonic acid and your phosphoric acids, what they like to do is they like to rip things off of other chemicals because they have these hydrogens. And guess what they like to rip off when you consume those? From your bones. Calcium.
Oh.
All right? And females are more prone to osteoporosis
Really?
than men.
Wow.
Yes. Especially young females. So be careful when you're drinking pop. All right? Be careful when you're drinking pop. So if it has phosphoric acid or carbonic acid, it's sucking literally the carbon out of you. This is why I drink Mountain Dew. All right? Because it's not phosphoric, it's not carbonic, it's citric acid. So, one of the better acids because it's a fruity acid, which you find more in fruits. So, be careful. Be careful with that. Let's talk some weak bases. Do I have any farmers in here? It's funny that Jack says that because I just got an email today from AP talking about the 2023 College Board National Recognition Programs. Congratulations to Jawei G and Jack Pomfret, also Reese, for getting the NRSTA award.
What's that?
Which is the National Rural and Small Town Award. So there you go. Congrats. I don't know what that means, but you got it.
I got it.
All right.
A little certificate thing I can print.
NH3.
I'll be honest.
NH3, NH4OH. These are usually your cleaners that you use, and farmers use these for fertilizers. So, I don't know if you guys have ever heard this story, but there was a guy in southern Ohio, and they use ammonia for their fertilizer. He was driving his tractor, pulling his tank of ammonia. Have you ever seen the tractors in the field with like biohazard, like those big signs? It's ammonia, all right, that they spray into the fields because it has a high nitrogen content. This guy's driving his tractor. He gets on a hill. He flips, all right? The tractor pins his leg onto the tractor. Ammonia starts leaking. He's in a valley. Thing is, he knows his chemistry. He knows that ammonia is super dense. So he knows that the ammonia gases are just going to collect in this valley and suffocate him. He got out his pocket knife and slowly
That's crazy.
sawed his leg,
Bro thinks he's in the salt.
climbed up to the road, and lived.
Wow. What is
All right? And he knew that ammonia, it would have killed him, the gas. All right? It would have killed him because it would have got down there. He climbed up. He did like a Saving Private Ryan, and that guy survived. All right? It's better to be down one leg than to be dead. Just saying. So, what would this look like chemically wise? So, HNO3, that's a strong acid, plus water, plus H2O. That's going to give you H3O plus NO3 minus. So nitric acid plus water gives you, anybody know what this molecule is called? Hydronium. H3O plus is called hydronium, and an ion, a nitrate ion. Or if I just take HNO3 by itself, that's going to break up into H plus NO3 minus.
How do you get 3?
How do I get 3? Because that's what hydronium does. This water is accepting this hydrogen. So my water here is this is acting as an acid that's a base. Because remember, a base accepts a proton, right? And an acid donates a proton. Water can be both. We'll talk about that. All right? Water can be both. We will talk about that. Okay. Can I flip the page?
Wait, hold on.
Just H plus NO3 minus.
H plus NO3 minus. Okay. So we're going to talk about net ionic equations. Something new. All right? This is net ionic equations. EQUA. Okay, net ionic equations. So, when you do net ionic equation, there's always 3 parts. Step 1 is going to be a balanced equation. A balanced equation. So let's start out with something like AgNO3, AgNO3, states matter here. All right, states matter. AgNO3, AQ. AQ means it is soluble. Okay, that's aqueous. That's what the AQ in parentheses means. So that means this is a liquid, essentially, that I'm putting in. Well, it's a solution. I shouldn't say liquid. Plus NaCl, aqueous. So salt does not have to be a solid. You can have sodium chloride mixed in water. That's a solution. Yields, what's that going to give me? NaNO3, which is AQ, plus AgCl. Look at the back of your periodic table. Look at the back of your periodic table. On the back of your periodic table, you should have a box. There's several boxes, but there's a box that says solubility rules. Solubility rules. This is something that you're going to have to know before this chapter's over, but it's super easy. All right? It's super easy. Well, actually, you don't have to know because this is on the back of your periodic table. That's stupid. All right? You always have this. Nitrates are soluble. Most salts contain an alkali metal. Ions are soluble. Most chloride and bromides are soluble. Exceptions, salts containing silver, lead, mercury. Most sulfate salts are soluble. Most hydroxide salts are only slightly soluble.
What makes something a salt?
A salt?
Yeah.
Just usually like metal, non-metal, a salt.
Oh.
So here we have silver chloride. So silver chloride, is that going to be soluble or not soluble? Rule number 3. Exceptions are salts containing silver, lead, and mercury. So this is not soluble. So what am I going to write there for my state?
Solid?
Solid. That means it is solid. So this is my precipitate. That's my precipitate, and sometimes you'll see an arrow going down. Sometimes you'll see an arrow going down to represent a precipitate, because usually the precipitate goes in the bottom. So that is my balanced equation. That's already balanced. It's all 1 to 1.
Wait, is it assumed that this is like in water or is it?
If it's AQ,
Yeah.
yeah, you assume it's just a solution in water.
Okay.
Solution in water. So that's my balanced equation. Step 2 is my total ionic. My total ionic equation. Now I'm going to break this into its ions. So we have to figure out, number 1, does it break into ions? So AgNO3, that's AQ. Will it break into its ions? Yeah, because it's AQ. So this is going to be Ag plus plus NO3 minus. Plus NaCl, will that break into its ions?
Yes.
Yeah, because it's AQ. So plus Na plus Cl minus. Yields NaNO3 AQ, will that break into its ions? Plus Na plus NO3 minus plus AgCl, can I break that up?
No.
No, it's a solid. So plus AgCl. Now, this is a pretty basic example because I have no subscripts and I have no coefficients. So if this would be like 2 AgNO3 parentheses 2, then I would actually have 2 times 3, 6 NO3s here. So you do have to multiply through. But I'm starting out with a really basic one to start. All right? So that's my total ionic. Now, I have to determine spectator ions. Spectator ions. If you're a spectator, what are you doing? Yeah, so these are ions. Where am I going to find these? On? Any guesses? Ions on both sides of the equation. They're spectators. They're not the movers and shakers. They're just floating in solution, not doing anything. They're not reacting. So I put a box around spectator ions because I like to box my spectator ions in a problem. So do I have Ag plus on both sides? Nope. Do I have NO3 on both sides? So I'm going to box this, and I'm going to box this. Do I have Na on both sides? Yes. So I'm going to box that, and I'm going to box that. Those are my spectator ions. Those aren't really the root of what's happening in this equation. That's my total ionic equation. Step 3 is my net ionic equation. Here you're just writing what's left. So you write what's left and make sure it's balanced. So I have what? Ag plus on this side of the arrow, what do I have? Plus Cl minus yields AgCl. In a net ionic equation, charges must balance. Charges must balance on sides. This side of the equation has what charge?
What?
What is plus 1 plus minus 1?
Oh, it's neutral.
0.
Anyways.
This side of the equation, you're scaring me, has what charge?
Neutral.
0. So it has to balance. All right, it has to balance.
So when you're doing this, are you finding the precipitate?
Essentially, yes. You are finding the precipitate or the liquid. Or the liquid.
Okay.
Or the liquid. Let's do another one. Let's do a weak acid example. So here's a weak acid example. Let's do acetic acid, HC2H3O2, plus, and that'd be AQ, plus NaOH, AQ, yields NaC2H3O2. You tell me, AQ or solid? Is that soluble? NaOH. And I've got NaC2H3O2.
Yes.
Yes, that is soluble. AQ. Plus what? What's my other product? I have H and Na switching spots, so that's going to be HOH, aka water. For water, what state is water? Liquid. So that is L. You take the L for water. Sorry, our fancy cursive L. There's my balanced equation. Next step, total ionic. So here we go. It's already balanced. Will this break up? HC2H3O2?
Yes.
No. It will not break up. Why?
It's a weak acid.
It's a weak acid. So this is where knowing strong versus weak acid is really important. Strong acids do what?
Completely dissociated.
Yes.
Completely dissociate. Weak acids want to do what? Stay together. So that's where it's really important to be able to identify the difference. So I'm going to have HC2, H3O2 staying together, plus, will this break up?
Yeah.
Why?
Because it's,
NaOH is a strong,
yeah.
it's an alkali metal hydroxide. So plus Na plus OH minus yields, will this break up? It won't.
Let's check the rules.
Look at the rules.
It's an alkali metal, so it should be soluble.
This is soluble. So that yields Na plus C2 H3O2 minus. Will water break up? No, it's going to stay together. Plus H2O. Okay, figure out your spectators and write your net ionic equation. Write your net ionic equation. It's kind of fun because it makes sense when you write it, because you actually see what's happening. You actually can see what is happening. So I have HC2H3O2 plus OH minus yields C2H3O2 minus plus H2O. That should be your net ionic equation. Charge on the left side is -1. Charge on the right side is -1. So the charges are equal.
Hypothetically, you did it wrong, you'd know.
Yes, that is exactly right. If you do it wrong, your charges are not going to balance. And sometimes you have to balance down here. Sometimes you have to have like a 2 here, all right, if you need to balance it. You'll know when you get to it. Try this one on your own. Let's do strong acid. So let's do a strong acid. Let's do a strong acid. All on your own. HClAq plus NaOH AQ yields NaCl AQ plus H2O liquid. Write the net ionic equation for that. Is it unbalanced? That's NaOH. Do you think anyone will actually bring snacks tomorrow for day 2 of notes?
I'll bring a snack.
Okay. No, it's not.
Girl.
Megan, what?
I can definitely eat while I'm taking notes.
Hard to take notes on.
What did you say, John?
Like, I guess it depends on what you're eating, but if it's like, if you're eating.
Well, it's not going to be like eating a bowl of chili, all right? I'm saying bring like something like snacky, like
Hot Cheetos. I don't want hot Cheeto dust all over my notes.
you don't have to eat it.
I'm trying to eat.
Jack, that was.
But if it's like I'm in
Maggie, I saw your dad at the fair, and he took one of his like classes, and like I could just tell it was like culture shock for a lot of them. Like those East Coasters when they go to the fair, like it's just like it was fun watching them. And he bought them Lurch's donuts.
I know. He didn't even bring the money for it.
Oh,
Yay.
well, you guys can get them anytime, right? I understand. Okay, HCl doesn't break up. Why? Strong acid. So I have H plus Cl minus plus NaOH does it break up?
Yes.
Na plus OH minus yields NaCl does it break up?
Yes.
Why?
It's an alkali.
Yep. Na plus Cl minus plus H2O. Spectators are Na, Cl, Cl, which means our net is kind of cool. What did we make? Yeah, that's all we did. All right, this is a neutralization reaction. It's a neutralization reaction. Anytime you put a strong acid and a strong base, you end up with a salt and water. You end up with a salt and water. So, +1, -1, charge on the left side is, right side, neutral. So, where are we going with this tomorrow? So that's net ionic equations. It's not super hard. There is always at least one net ionic equation on the AP test. Easy points. And you know what? Most people can't do it. Not from Worcester, but people around the world for some reason can't do it. It's not hard. Tomorrow, we're going to take molarity, and we're going to do some stoic with it. Molarity is symbolized by uppercase M. Uppercase M. Anybody remember what molarity stands for? Yes, it's the number of moles of solute. The number of moles of solute over what? It's moles per, we're talking about solute, yes, per what of solvent? Liters. Per liters of solution. Per liters of solution, of the whole solution.
I literally said I was not locked into it.
So this is moles per liter. So moles per liter is where we are heading tomorrow with this. So tomorrow we're going to combine all of this into what we were doing last chapter.
Okay.
So you're going to have to do limiting reactants. You have to do the concentration of all remaining ions. So this combines, once again, everything we did last chapter will be combined into doing this tomorrow.
I apologize to both of you because I've been really salty these past 2 weeks.
So that's a good point to stop today.